Okay, so hello everyone. My name is Niv Cohen. I'm a PhD student of Dr. Yedid Hoshen that just spoke. I've been working mostly on anomaly detection, a bit about disentanglement and other things. I will be finishing my PhD hopefully this year, so still need to figure out what to do after that. And I think it's time to move to the practical session. So we'll start with a short presentation, both like emphasizing the key points that we'll need for the practical session and like pointing to what we will actually do there. So let's begin. So as I said, what do we try to do in anomaly detection? We try to separate between the known and the unknown. So the known, by the way, for those of you who are taking pictures, you are most welcome, but I will also share the slides. So
thank you.
It's up to you if you want to.
He enjoys taking pictures.
Okay, and I'm also like, you also get to see me in the picture. I mean, not in the slides. Okay, so we have some known class, in this case, this good hazelnuts, and then anomalous samples. The anomalous samples could be anything. They could be hazelnuts with some defects on them, a cat, a flower, and so on. And now we get some new sample, and we want to say, is it normal or an anomaly? And we can also see that this hazelnut with some paint on it is more normal than the cat in terms of how much is it as an hazelnut, but it's not completely normal. So we want to measure some distance. And as Yedid said, the main tool that we have is a strong representation, and we will use ImageNet pre-training. So ImageNet is this huge data set with 1,000 classes and 1 million images, and really large computer vision models are trained to classify ImageNet classes. And through learning how to classify ImageNet classes, they usually learn what is important to humans, what defines an object, and they also learn what do we want to ignore. So if, let's say, we have a chessboard, and now we have the inverse of a chessboard. So as vectors, these images are really different, but they are really similar to us as humans. So this is the kind of similarity that the ImageNet pre-training gives us. The network kind of have a feeling for what is important for us. And we can analyze this network. People have done it in many works. So usually the low-level features learn this kind of wavelet transforms or Fourier features. And the more high-level are more semantic. The higher levels are more semantic. They kind of learn more semantic patterns. Maybe you can recognize some object or some patterns in them. And here in this exercise, we will focus on detecting objects. So we would want the higher, the more semantic levels. And we take them from the penultimate layer. So we have this kind of a big layer. The last layer of the network is the classification part. So the weights here says to which ImageNet class are we belong. But we are not interested in ImageNet classes, so we take one layer before that, which kind of gives us the most abstract representation of the object in each image.
Why is that? How many dimensions?
So this usually have like, in the network that we will use, it has like 2048 dimensions. And there are a lot of work that show that this representation from here is really like, have a lot of interesting properties. Maybe there are some direction in the representation which corresponds to concepts that are semantic to us as humans. And just as a disclaimer, as in many deep learning tasks, but especially in anomaly detection, objects are not like mathematically well defined. We can all think about like a tiger. It's not I don't have a closed form mathematical formula for what is a tiger. So in one sense, this is not everything we will do will be mathematically principled, but key insights do generalize. The kind of things that will work for images will also work usually for time series, language, and so on. And also 99% we usually consider a great performance. Now for some application, maybe some medical application, like 1% of error is too much, but in most cases that we deal with, 99% is a great performance. Okay, so let's start talking about what we will actually do. So we'll start with further discussing the setting, then we'll talk about image anomaly detection, segmentation, and then we'll go to the practical exercise. So the semester of the setting, we only assume to get the normal data during training. So let's say the blue points are the normal data. And it's kind of challenging to build the classifier, but here we need to build the classifier between the blue points and say the yellow points. But then in training, we only get to see the blue points. So in some sense, we need to guess what the other class would be. And this task where we get only the normal data is very practical for various reasons. So we can think about cybersecurity attacks. So usually the most interesting and the most dangerous cybersecurity attacks are exactly the ones that we do not know to expect in advance. So this is one thing, and also in science, usually the most interesting discoveries are not like classifying between two kinds of hypotheses, but discovering something which is completely new. And okay, now we want to evaluate our performance. So we have some anomaly scores for the anomaly and some anomaly scores for the normal data. And we want to distinguish between them, but there are two kinds of problems. One is that we need to choose a threshold in order to measure the accuracy. Another problem is maybe in our test set we might have like different balance between the classes. Maybe in this weird test set we have much more anomalies than normal. Oh, I think I switched the labels here. I forgot to, but anyhow, we might have imbalance in between our classes, and we want a metric that do not care about the balance between the classes in the test set, and more importantly is like agnostic to the threshold that we choose. So this is why we use the ROC-AOC method. In the ROC-AOC method, we use different false positive rates, like different amount of normal data that we are willing to mistakenly consider as normal, and we sweep across them, and for each false positive rate, we measure the true positive rate that we can expect to find. So, for example, if we are willing to get a false positive rate of 20%, we might get a true positive rate of 80%. And the random classifier gives us 50% because we can just give random scores to all the samples, and we'll get the same percentage of false positive rate and true positive rate. I know these kind of terms are a bit confusing. We can do some meditation about them later. But actually, there is a very nice interpretation of ROC-AOC, which is much simpler in my opinion. Okay, so let's say we have some anomaly detector, and we have the normal data and the anomalies. So we can take a random anomalous sample and a random normal sample, and ask what is the probability that the anomalous sample would have an higher score than the normal sample. And I like this interpretation. First, it's really easy to see why 50% is the baseline, because this is the probability with random scores. Also, it's easy to see why we don't care about the size of each class, because we just take a random sample from each. And the way that we can understand this equivalence is like taking a random normal sample is kind of being on a random place on this axis, and a random anomaly is kind of being on a random place on this axis. And if you're interested in mathematical details, we can look at it later. Okay, so now let's move to actually doing image anomaly detection. So as Yedid mentioned, we use k nearest neighbors. We take each point and we measure its distance to the k, maybe 5 nearest normal samples. And we expect that anomalies would be found in low density areas, and they will therefore have a large k-NN distance. Quite embarrassingly, this is the state of the art on tabular data. There are a few methods which do around the same. And in the first part of the notebook, we will just use it for tabular data. It will be very easy, maybe 2 lines of Python. There is a long code that loads the data, but I try to hide it. So this should be really easy. And actually, there is only a single parameter here, which is k. So I guess some of you have heard of the bias variance trade-off, and if you didn't, it's quite intuitive. So let's say we want to fit some data. We can have a low amount of, like just few degrees of freedom, and then we cannot fit the data very well, or we can have like many degrees of freedom, and then we can fit the data well, but we won't generalize. We can't actually estimate all these coefficients with few training points, and we can do something which is about right. And in supervised learning, usually we have some validation set. We keep a set outside of the training set and use it to find the optimal trade-off. And now I have a bad news and good news. So the bad news is that in anomaly detection, we never assume to see even a single anomaly before inference. So we cannot use any supervised method to find where are we in this optimal trade-off. The good news is that KNN is quite robust. So you could play with it in the network, you could use a k equal 1, 2, 20, and it all gives about the same results. And, but just to think about it, if we use like a very small k, we are more to the high variance side. It's hard for us to estimate the density in a like very local accurate way if we have only a small number of points. But if we use like a very large k, maybe we just estimate the distance to the mean, so we estimate it very well, but it's biased because our density is not that uniform. Okay, and now I will, any questions until now? So now let's talk about the Panda, the work that uses pre-trained features for images. So we would like to do this very simple KNN method to deal with anomaly detection in images. But images, as other data modalities, live in a huge dimension. So for example, it can be 256 by 256 by 3, it's like almost a million. And if we have only like 1,000 or 10,000 samples, those samples will be very sparse in this huge vector space. So we actually want to embed these images into a lower dimension, but not only to a lower dimension, but also to a dimension which is semantic, which cares about the properties that we as humans care about. So as we said in the motivation, we take a pre-trained ResNet, we use the pan-ultimate layer, and then we get these vectors, which are of dimension 2048, 48, and we do the KNN estimation on them. And as you did mention, this very simple baseline was already enough to achieve the state of the art at the time. And we will talk, like in my example, we will work on the CIFAR10 data set, in which we have like 10 classes. We take one class, for example, the horse as the normal class. In Anomaly is anything coming from the other classes. And then you could also try your own data. And as also mentioned by Yedid, we can generalize far beyond like the training set of ImageNet. So one could say, okay, ImageNet got to see them in training like cats and dogs and cows and rabbits. And it's no wonder that it can distinguish between these kind of classes. But we try to use it on like medical imaging and satellite photos and like industrial photos, and it gave us state of the art on all of these data sets. That's it. Okay, but now we can ask, can we do better? So I told you we can take images, we can use the pre-trained features, and just get some very strong baseline. But maybe we also can use our data set that contains maybe 1,000 or 10,000 images to fine-tune our metric to better describe the normal data. I also included in the collab links to the more complicated methods that give better results, but there is a very simple method which gives very good results and even sometimes the state of the art, which is a linear whitening. So we can think about our original data from coming from this kind of distribution. And as was discussed in the questions, maybe if we have this kind of weird shape, if we deviate in this axis and we deviate in this axis, we get like different importance. Maybe we regard this as more anomalous in this thing. And maybe it's better to give equal weights to all the axes. So we just multiply our data here by a linear matrix. And this linear matrix gives us the same data but with the covariance matrix of 1. And this already gives some boost to our results. And some of the more complicated methods, this is also a good intuition to think about the more complicated metric adaptation method. So again, when we come to estimate the covariance matrix, we have this bias variance trade-off because this matrix is huge and we don't have as much data as we want to correctly evaluate what the matrix is. So we use a shrinkage. It's a simple trick that kind of mix between the empirical covariance and the identity matrix to give us a better estimation of the covariance. For the more mathematically inclined, I also included the link that explains more about shrinkage and why it works. I find it very interesting, but if you're not interested, it's not very important for us. This is like a single line of Python, and we will do it without getting into the details. Okay, now before moving to the session, let me talk about anomaly segmentation. So anomaly segmentation, we are interested not only in it's saying, okay, there is something anomalous about this image, but why? We want explainability. So maybe this B is the thing that is anomalous about this image, and we can compare about them and get the segmentation of the B. And to do so, we create a feature descriptor for each individual pixel. We do it by combining the more semantic high levels of the feature of the network and features from the low levels, which are kind of more Fourier transform. And together, this give us a very strong segmentation results. And I did not include like this specific method inside the Colab, but I did include links for the GitHub project, which are quite easy to run. And if you are interested in this and have some questions, you are most welcome to talk to me about that. So can we always use transfer learning? So not always. So in image and video, we usually can, also for language. For time series, sometimes we can use it for audio, but not in other cases. And for tabular, not. So we don't have good transfer learning for tabular data. Even, I think it's fair to say we don't even have a good deep learning method for tabular data. Okay, so the main messages is that anomaly detection relies on strong features. Pre-training is great when it is available. And fine-tuning can bring significant gains. In fine-tuning here we'll use the linear whitening, but there are also more sophisticated methods you might want to try out. So practical tip just in the notebook. So when you would want to load your own data set, you would do it with the P library. You want to do this transform to the images. It's all, you can all see it in the code, and we can go over it together. And feature normalization is also always something that is worth trying, just taking the features and normalizing them to the unit vectors. But like you shouldn't be scared of any of it. You will all get it written, and we will go over it together if you want. Okay, so now it's the moment we've all been waiting for, so you can scan this QR code and get a link to the Colab notebook. The notebook starts with loading and doing anomaly detection on tabular data. Then we move for anomaly detection for images. So we load the data, do the density estimation on the raw images as vectors. And then we see we get much better results with deep features. And then we add the simpler metric adaptation. And then we will try our own tabular or image data set. So if you have any data set from your research that you would like to try, that's great. And if not, we can just collect photos with our camera from our phone and kind of guess which one will be found as the most anomalous. And when you open the Colab, please use the GPU because it will make things faster. So any questions until now? Was it too fast, everything?
It was good. It was
Okay.
aligned with what I said.
Okay. So after everyone that wanted scan the QR code, please let me know, and maybe I can also open the Colab on my computer. Another thing that we have a lot of parameters in a notebook. You are most encouraged to tweak them, try different values of Ks, different classes, different shrinkage ratios. But maybe it's more exciting to try your own data. So I leave this up to you. So is anyone still scanning? Okay. And really, I'm here just to answer your questions. Please come with questions like about general anomaly detection, about specific line in the notebook that you need help with. Oh, and another thing, if you want to save your notebook, please save a copy in your drive. So download the notebook, you say, save a copy in my drive, and then you can save your changes. Did somebody was able to open the, okay. סליחה להריץ?
כן, כן.
כמובן. סליחה.
יכולים לעבור ביחד על הדברים?
אם אתם מעדיפים אז כן.
אני לא יודע.
אם אתם מעדיפים לעבור ביחד?
Maybe in English.
Oh, okay. Is anyone prefer that we go over things together, or are you all?
I think it would be better because you just see the coding.
Yeah, in previous sessions, you show what you put and you let people play with.
Oh, okay, so close. Okay, so we start by downloading the data. This is not the most interesting thing.
Someone didn't make a copy.
Okay, so let's do it without GPU for now. Yeah, so we should all like copy the notebook. Okay, so the interesting part starts here. So we start by loading the dataset. This is some medical dataset called arrhythmia. And we just load the features and we see their dimensions. Like we see that each, the training samples, we have like around 200 samples or 250 for the test. And each sample has 274 dimensions. So let's start by just plotting, doing a t-SNE plot of the features. And we can see that they look something like this. Sometimes this t-SNE has some randomization to it. This is a better t-SNE plot. And okay, and now we want to do the K and then the density estimation. So in this function, we just plot the different graphs. So we'll show the results of this function in a second. So start with a simple K-NN density estimation. And here we first just use this skNN library to create an object for a K nearest neighbor density estimation. We fit it on the training data. And fitting is nothing like very sophisticated here. Fitting the data just means that we keep all the data inside the memory of this object to do the density estimation later. And then we can simply do it on the test data. And we care about the distances. It also really gives us the nearest neighbor of each sample, but we care what is the K-NN distance. And then we do the mean over the, in this case, 20 nearest neighbors. So we take the mean of the distance. And we clip it just to have a nicer plot later. And we can have we can show like three things here. First, we see the distribution of the distances of the normal data and of the anomalies. Then we have this ROC curve. So for each false positive rate, we get to see the true positive rate. And we get to the ROC AOC, which in this case is 78%. And if you would like, you can change the data set. So now we can change it to another data set. For example, like this. So the t-SNE plot will take a bit longer, but I would say that this is the point where you can just enter your own data. So you can just take your own data and give it into these two variables and run this simple function. And let's see if the t-SNE plot is ready. We see this is a much simpler data set. The anomalies are quite separated from the normal data. And let's see how does it do in terms of ROC AOC. So here, okay, so maybe we want to look at it on a finer resolution. Okay, so we don't have much anomalies, but we can see they are more separated. We have a much better ROC AOC curve, so we can get a very good detection of the anomalies without getting almost none of the normal data in. And we also see it in the ROC AOC. So ROC AOC just stands for ROC area under the curve. It's the area that we have here. So if you have any question about the tabular data or the metric, this is a good time. So now we can move to images. So here we choose some class for the CFR10 dataset. So we can like use the first class. We train the data. Sorry, we don't train. We just here we load the data. We just calculate the labels. We say that the label is 1 if it is from any other class, and 0 if it's from the class that we chose. And we can also downsample the data if we want, just to make things like run faster, or like to challenge the method to see how it works with less data. So this is an example of a big image from the normal class. This is an image from the anomaly, an anomalous image. And here we just take each image, we convert it into a vector, and like just a concatenation of all its pixel values with all the colors. So we can see we end up with a vector which is quite long, and we can do anomaly detection based on density estimation just on the images as raw vectors. It will take a little bit of time, but eventually we will get it. Okay, so we can see that there is a significant overlap between the two classes, the normal and the anomalies, because examining images just as raw vectors is not like very distinctive for the attributes that we as humans care about. We can see that we get some anomaly detection performance, but it's not very impressive. And now we can use it with the deep representation. So I think this is the stage where we need the GPU. So here we just load the network. This one line gives us the pre-trained network. Here we just ask for the penultimate layer of the network for the features. We need to put this network in evaluation mode. This is just a technical detail of a PyTorch library. We convert it to CUDA. I think it won't let us because we don't have the GPU available, but you would have it. Then we do this transformation. We just take image and rescale it to the sizes that the network expects. And also we normalize each pixel by some mean and standard deviation colors. And in this function, we just get the features. We feed the network batch by batch of images. And we get the features, and we normalize them. So we can also try to like use or not use this normalization and see the effect. Then we convert it. We call it this function, and then we just do this anomaly detection density estimation as before, but with the deep features. We see significantly better results than using the raw images. And now we try to do the metric adaptation thing. One thing to do whitening is just to use the PCA fit transform, and PCA transform just whitening the data, as we saw in the presentation. But actually, we have a hard time estimating the correct covariance metrics. So later, when we do this with a shrinkage function, and we can go about details for the shrinkage function, but I'm not sure if it will be the most interesting for all of you. So we just need to set some shrinkage factor which determines the blend between the identity metrics and the empirical covariance metrics. And then we can do, this is sphering, this is the whitening with the shrinkage factor that we chose. And we can see that this already gives us better results. And actually, like, the difference is quite small, but if we use other classes, we can get like a significant boost from the whitening. And in the end, I included some links to better adaptation methods and the anomaly segmentation methods, and some initial lines that you can use to load your own data and try this kind of image anomaly detection on your own data. If you want to try the tabular data, which might be simpler, you just get like any Excel table, you load it to contain some vectors that are numpy, like numpy arrays of samples, and you can just feed it to this pipeline, which is essentially just these two lines are like the most essential, but the rest is just like wrapping them.
Do you apply this method to EEG or EMG, the signal, not just images and tabular?
So I think one of the time series datasets is of EEG signals, and we found out that first, this data set was not of the highest quality because just looking on the energy, like on the standard deviation of the EEG signal, like almost solved it. But we did find out that for such time series data, using k-nearest neighbor was still the correct approach. And what we do there is usually we look on different windows in the sample, and we measure the distance between samples as sets of windows. So we take a set of windows from each sample, we do a random projection on them. It's like a radon transform, if you happen to know it. We just take the set of windows, we project them with random access, and then we kind of measure the distance between the sets. It's kind of similar to it's not exactly, but it's kind of similar to the slice Wasserstein distance. So you look on each of the signals as a set of local windows and check the distance between the sets. I can refer you to the paper explaining the details about it if you're interested. Yes?
Do you think in question you can use FFT?
So I think, in my opinion, FFT is just like another kind of features that we can use for anomaly detection. I think that, in my experience, I think it wasn't the most indicative for the kind of data set that we were interested in. But if you have some signal, maybe, so for audio we have other solutions, but maybe you have some signal and you find that the FFT representation is the most indicative representation for what you care about in this signal. So yes, doing FFT and then nearest neighbor on these features might completely make sense.
What about using a foundation model, I don't know, wave to wave or something like that, from one domain like audio, using a different domain, like any signal?
Yeah. So actually I was trying to apply some method that were developed for audio on other kind of signals, and they did not work, at least on the data set that I tried. But I think it's kind of question of how similar is the signal, because we see in images that we can take something which was pre-trained on ImageNet and use it on aerial images, and it works completely well. So I think maybe if your signal is another kind of audio, maybe not human voices, but like audio taken from industrial equipment, so using like wave to wave would make would completely make sense. If your audio is maybe, I don't know, some astronomical data about orbits of planets, maybe I would guess that wave to wave wouldn't work as well on it, but it also makes sense to try. Does anyone have already in mind the data set that he wants to try? So maybe I can ask the following question. We have this shrinkage factor, which tells us how much do we bias our covariance metric towards the identity metrics. So if I would increase or decrease the number of data, would I expect that a larger, when would I want the larger shrinkage factor? When I have a lot of data, when I have a small amount of data? So when I have a lot of data, I have like a good covariance metric, empirical covariance metrics. So would I want to use it, or would I want to mix more of the, like my prior of the identity metrics into it?
So you use the covariance.
Yes, so the shrinkage, if I had an infinite amount of data, I would never use shrinkage. I usually use shrinkage to compensate for not having enough data to correctly estimate the covariance metrics. So maybe someone wants to tell me something about his own research, which kind of data set does he use, and maybe he wants to think together if we can use them for anomaly detection.
I'm wondering if a gene expression data would work.
So I think it might work. So in gene expression for its cell, you have the set of genes that you want to use. So because it is quite similar to tabular data, I wouldn't expect deep representation to work especially well, but I think it makes sense that it would work, and especially because I guess this thing vary in order of magnitude. So if you know that a logarithmic transform on this data makes sense, you might want to use this. And of course, the whitening that we are doing in this network might also make sense.
And could I discard inside of 1,000 genes that I know are not relevant, and taking out features that I know are not, I don't want to ignore them.
Okay, so if there are some features which you think are just noisy, you don't care about anomalies in these 1,000 genes, yes, so getting rid of them indeed makes sense to kind of getting a better signal to noise ratio. Yeah, of course. So let's try together. Is it a tabular or an image data set?
Image data set?
Ah.
I'm not familiar with it. Maybe someone else knows it. Just for medical anomaly detection data set.
Mm-hmm.
Search MURA, M-U-R-A.
M-U.
Okay, try large data set for anomaly detection. Yeah. Abnormal.
Okay, let's see. This one?
Yeah.
Okay, let's see where we can download it.
There's a git in the previous page. Go down. No? Bit more? Yeah. Tell us a little bit.
Here?
Yeah.
No, this is that. Okay. So PyTorch one layer. Okay, that looks good. I think I would just need to open the collab from another user so that I will have the GPU. Okay. Okay, so let's start with just running the notebook so we'll have all the functionality. So but did some of you were able to run it and play with the different values of k and the different linkage factors, maybe change the cipher class that we worked on? You can try to do it while I'm waiting for this to be ready.
It's too much for fun.
Yeah, I'm trying to. כן? מה פספסתי? אוקיי. כן. Okay, I think maybe this is the stage when we give up. But another thing that we can do, we can just try to like crop a few of these data sets and see which one do we find as most anomalous. I know if we want to do it with this, or maybe we can maybe just look for images online. So let's choose one class. Which class do you like? Yeah, anyone. Give me something to look for images online.
Cats.
Cats. Okay, that's good. And okay, שמירת. Okay, so we'll just download. Why does it? Okay, so let's save. Ah, wow. So first I thought maybe I should get rid of this, but maybe let's keep it and see if we get to detect it as an anomaly. Okay. Okay. Okay, so we have our file, and then we can take the images. Okay, maybe something like this. Okay, so now we hopefully have this set of images. Okay, and we have all the features. Now we can try to let's start with plotting them. See if we get anything interesting. Okay, so here we don't have any labels yet, but we can. Let's see if we get. Okay, so this is our cats. We don't have much of them yet, so it's hard to say anything. But we can put in like some other another class. Which class do we want now?
Monkeys.
Monkeys. Okay. Let's see. Monkeys. Okay, so let's get back to our folder. Okay. One. How many monkeys do we have there? Okay. Four. Oh, no, that's not what I wanted to do. Okay, so now we have the cat images and the monkey images. Okay, so we have all our images. You can get the, let's call it, say this is the test features because we have already two classes. Okay. So, okay, this is still looking a little scattered, but let's see what happens if we look at the colors. Okay, so we see some separation. I think maybe one class is more clustered together and the other is not. So I think like the smallest data set that I hoped with for anomaly detection was maybe 30 images. I think maybe we can do something with 10, but it's maybe too much. Maybe we can just get some more images. Okay, and did we do any monkeys? Do you remember? Two of them. Okay, so I think they are still somewhat mixed together. Maybe more cats will do. So I think I hope that at least some of you are interested in reading the different shrinkage and different C14 classes. I think this is maybe the more interesting thing to do. I think if anyone is interested, we can try to put together that the probability equivalence of this row curve C curve. Does this interest anybody? Okay, so let's try another class. Let's try class number 8. And let's say we want to downsample it significantly. Let's say take only one of every 100 images. So we only get like, I thought I was asking for one. Okay. We need this. Okay, so now we really have a really small amount of data. So sheep is the normal class, and anomaly is again maybe anything. Okay, here this is also a. We also have sheep in the test. It is the normal data, but say okay, so we have some vehicles in our anomalies. So let's start with density estimation on the on the raw images. Actually, it works not too bad. Do you know why the rock RC curve here is already like not so smooth? Can someone explain this?
Yes, we have.
Number of images.
Because?
The number of images.
Yeah, exactly. When we scan different false positive rates, we are limited by just the number of samples that we have. Let's see if the features will do anything good on this. Okay, and you see that even with only like, I think we have only 50 samples, normal samples during training, still the deep features are giving us like significant boost in results. Let's see what happens when we try to do the simple linear whitening. So actually you see we get much worse performance. Why like this whitening that should have helped us give us like this very bad results when we do whitening with only 50 images? Any ideas? What went wrong? So what we try to do here is to estimate the covariance matrix with 50 images and use this covariance matrix to make the covariance matrix of the data identity. But we see that while it worked like fairly well, it didn't break anything when you use a lot of images. When you use only 50 images, it kind of gives us something which is quite catastrophic. Do you have any suggestion why? Okay. Okay, so two different is one thing, but the covariance matrix. Okay, so our feature dimension is 2000. What is the dimension of the covariance matrix? It's like something around 2000 squared, a little bit less. And what happens when we try to estimate this huge matrix with only 50 images? Do we get a good estimation of the covariance matrix? No, not at all. So doing this simple whitening with small amount of data is not very good. So let's try with the shrinkage. So now we use a shrinkage factor of 0.1. I don't know if it will work well enough for this kind of data. So now we have our covariance matrix, and we plot the score. Okay, so the covariance matrix fixed some of it. It's not as catastrophic as it used to, but it's still not helping us. Let's try in higher covariance, higher shrinkage value. Okay, and you see that like with higher shrinkage value, we only get much better results. Almost as similar to the ones that we have before. I think maybe even a little bit better. Yeah, even a little bit better, because now when we like mix between our empirical covariance and the identity metrics, we did not like try to estimate this huge matrix with only a few numbers of samples, but actually we got only like what we can get out of it and used our prior of the identity metrics for the rest of it. Okay, so I think that's about it. If you have like any other question, you're most welcome to. If you want to look later also at the notebook and ask question, of course, feel free. And especially if you're interested in other things as well, be it like time series data or anomaly segmentation, or maybe even other modalities, feel free to come to ask. You can approach me, like you can find my email online. And I would usually be able to refer you to the state of the art, or maybe tell you that the state of the art is just k-nearest neighbor on the raw data, because we as a species, we didn't go further than that on some level.
Thank you very much.